All right, so this is a review of NeurIPS, some of the stuff that I saw, and specifically I'll be looking at reinforcement in this presentation, other presentations looking at other subjects covered. So this was the first talk, Reinforcement Learning, Past, Present, and Future Perspectives by Katja Hoffman. I believe she works for Microsoft, is a researcher there. You can view this presentation online, and I have some notes. So overall, this talk goes from basics to like advanced stuff that I don't know. So one interesting innovation is very simple, which is average Q learning. Basically, you train a bunch of Q values on, and you train them to bootstrap off of some kind of average of all these different Q values. And so this reduces the variance, like target networks reduce the variance by averaging over kind of time. Well, multiple heads reduces the variance just like any ensemble does to improve stability and therefore performance. And they take advantage of the multiple Q values to use each Q value corresponds to a head in their neural network. So they pick one at random in order to make moves, adding a bit more variety to the state sampled. And there's something about Bayesian priors. I'm not sure exactly what they did there. All right, optimistic actor critic. So there's a blog post by Microsoft on this. So this is like soft actor critic, but it uses an optimistic bias somehow for exploration. So, and as you can see, we're getting much better sample efficiency, and maybe the final performance is even better here as well. And this is on the humanoid. Yeah, so one problem with soft actor critic, which I've been trying to figure out, like, how can we improve this, is that soft actor critic is pessimistic, right? When it's uncertain, because it takes the minimum of those two, what would they call? Basically, it takes the minimum of two Q functions. They aren't Q functions, it's all, they're optimizing entropy as well. So that makes it pessimistic where it's uncertain, which means, and where it's uncertain might be where you want to explore, right? And so this can help it not optimize over the errors in your policy and therefore make bad decisions. This pessimism can be helpful in that respect, but it can also mean that we end up not exploring important regions of the space. And I think these OpenAI gym environments, like the humanoid, their reward structure has been shaped to make it easy to learn, which means presumably there aren't these local optima where there's a better global optima somewhere else. So I'm thinking maybe where the reward shaping hasn't been as good, so there's more in the way of local optima, maybe optimistic actor critic would actually work better in that case, even better than soft actor critic. So this, for some applications, this might be quite useful. So distributional RL was mentioned as valuable. I think they might have used it to implement the optimism bias. I haven't learned distributional RL, it's kind of on my radar. So that could be something that's useful to learn. So this was one of the, I think, highlighted talks. So it's a variational inference approach to reinforcement learning. So you're keeping track of the uncertainty, and therefore you can do better at exploration versus exploitation again. Exploring when the uncertainty is high. So this looks like it might be useful. Yeah, I'm not sure why it wasn't highlighted even more in the conference. I'm not sure if it has some limitations. So unless it seems like exactly what I or you need, my thought is just wait a little bit longer, see what cites it and what improves on it. So this was interesting to me, the successor representation. It was new to me. So this is the successive representation where you're starting at state S, you're taking action A, and it's for the state S prime. And so basically here, so we've got an indicator that we end up in state S prime at some future time with discounting here, and then we add that up over all future times and take an expectation. So this is basically you're getting a reward of 1 for being in the state S prime, right? So you can think of this is kind of like a Q function where the reward just depends on, you get a reward of 1 whenever you end up in state S prime. So that's interesting. Well, why is this so helpful? Well, we can combine these to represent any arbitrary state-based Q function. So as long as the Q function only depends on the state, we can encode the Q function like this as a combination of these successive representations. So we're doing something kind of like Q learning here, but then we have generality, where different tasks might have different Q functions, right? And so then we can just change what we're optimizing here, and we can use the successive representations we've already learned with different weights and quickly adapt to a new task. So model-based approaches also have this strength, I guess, but with model-based approaches, you then you look into the possible future using your learned model to figure out what to do, which could be quite expensive. This would be much cheaper. Yeah, so I'm not totally sure of the strengths and weaknesses versus a model-based approach, but an interesting different approach. All right, so this was actually, I think, from the meta-learning workshop. Basically, the takeaway is that transformers have now been made to work for RL. It makes sense that we've got something unfolding over time, and something that happened a while back might be useful later on, right? And transformers should be, or attention in general, should be excellent at picking, like having that memory. It should be able to pick up on something that happened in the past when it's relevant to a current decision. Unfortunately, or well, initially at least, transformers were unstable and they did not work as well as LSTMs. And so it seems that they've figured out why. So although vanilla transformers totally failed, they got a non-vanilla transformer that addresses the issues and works very well, like better than LSTM. So one of the things that made it work is removing the residual connections outside of the layer norm. I don't understand the details. And they added a GRU type gating mechanism for residual connections. And this was important after they did a bunch of ablations. So I found this quite interesting as well, just like this approach of like, well, what really made the difference? And I like that they're being very careful about that, about investigating the causality of what made the difference in making transformers work. All right, so I think this is Sunday, I think, at NeurIPS. So this is an entire day workshop focused on RL. And my overall takeaway is RL continues to advance at a steady clip. Nevertheless, PPO is still widely used and is winning most competitions. In fact, almost all of the top entrants used PPO. So PPO is the way to go, it seems, unless you're really looking for sample efficiency, in which case soft actor critic is still the baseline against which new sample efficient methods are benchmarked. So it seems like soft actor critic is pretty good, but there are improvements being made that, at least in certain problems, they seem to perform better than soft actor critic. State, right. But this was quite interesting. This is state-based importance sampling. So the basic way to do importance sampling in RL would be to use use trajectories and say, okay, under the current policy, my probability of following this trajectory would be this. Under the policy it was actually collected on, it would be that. And so let's factor in the ratio of the probabilities and do importance sampling that way. That is going to be much higher variance than if we can actually say, okay, what's the chance that we get to this state under the new policy versus the old policy? And so they figured out a way to estimate the proportion of time spent in each state under different policies. And then using this, they can get this much lower variance. They can do this much lower variance importance sampling than trajectory-based. And so they demonstrated some excellent sample efficiency, better than soft actor critic. So they're just doing basic actor critic, I think, with importance sampling so that they can reuse old data. And but I think the problem they were demonstrating this on was inverted pendulum, which seems like a pretty toy problem. So it seems like there might be some limitations to the complexity of the environment that this approach can handle so far. Yeah, I think they might have worked with, there's this HIV simulation data set as well. I think they might have worked with that. Yeah, so also you can do a lot of learning with this approach. You can do a lot of learning on a fixed data set. So this is an even stronger, this is even more impressive than off-policy learning. This is totally offline. There's no new samples at all, right? So yeah, they gave some examples where like they just use a random policy, collect a bunch of data, and then they use that data with importance sampling and actor critic with this version of importance sampling and actor critic, and they train a policy that actually works quite well. Distributional RL for optimism. So distributional RL allows you to estimate like the whole distribution of rewards, right? And so I think basically what they do is they take, okay, the few most negative rewards, they just like chop those off, pretend those didn't happen. And then they replace those with a certain probability of getting like the highest possible reward in your RL problem. And that's how they implement optimism, which is, optimism is a far better way to explore than epsilon greedy. It's far more targeted. And so technically that shifting the probability, this is equivalent to shifting the CDF, the cumulative distribution function, down. So now your probability adds up to less than 1, so then you have to add that extra probability at the maximum possible reward. And they figured out some approach of doing risk-adverse optimism. So optimism that will help you explore, but you won't crash the car that you're using to learn. So it's important that we explore effectively and that we don't do the really stupid, costly things, that we don't explore those outcomes as well. Some interesting RL tasks, the cart pull task, a very simple benchmark. For HIV treatment, there's now a simulator, and so they were applying different algorithms to the simulated HIV treatment. And lastly, blood glucose control. So this seems like a really promising application because as long as you don't pump too much insulin in, and maybe you make sure you pump enough as well, you're not gonna kill somebody, you know. And what they found is that they can, with far fewer samples than kind of like you could have a rule-based policy for how to output the insulin, but they can output far less insulin with a machine learning RL-based policy that's customized to each individual. So yeah, this seems like a very promising application of RL. Um, this seemed quite interesting and unexpected to me, that if you use atom with DQN, you actually get much better performance than whatever optimizer, probably SGD with momentum, that they were using before. Now, I have no idea why. I think you'd have to drill into this, but your optimizer can obviously can make a difference in your performance. So it turns out that adversarial attacks are also an issue with RL. And what you can see here is there's a normal opponent here, and the normal opponent punches the victim. And so this is kind of a normal way of opposing the blue player. But here, this is an adversarial opponent that has been trained to defeat the victim without the victim having an opportunity to train to respond. And you can see the approach here is just collapsing a little ball on the floor, and the blue ones, their input to their neural network is so different than anything they've trained on. Whoops. Wrong way. The input to the neural network is so different than anything they've trained on that the blue player just falls down. And so the red player has a much higher win rate. So the blue player has a much lower win rate when red does this. So basically, red is using its body to create an adversarial image to defeat the blue player. There's another example with the soccer shootout and similar kind of strategy. Goalie just falls into the ground and wriggles around. So funny, but also this would be a real thing to keep in mind. Could there be adversarial attacks? And if so, this is something that to take really seriously when implementing RL in the real world. So there's a talk about improving generalization in RL. In RL, often we don't worry about generalization. You have a certain environment, try to get your RL agent to perform well just in that environment, which in some cases, that's all you need if you have a very controlled environment, right? But ultimately, it'd be great to train agents that can generalize to new environments that they've never seen before, right? And so there's a few approaches. So one is regularization, so L2 regularization, dropout, those kinds of things. These help a bit. Domain randomization works, of course. If you can simulate a whole bunch of different environments and have more diversity that way, that's going to help you. But we don't always have access to this, right? So another interesting approach was imagine that you're training on images, right? So you have a CNN. And so what you do is you just add one more layer at the start of your CNN, which maybe maps 3 colors to 3 channels. So basically 3 colors again. But that initial layer has random weights. And every time you train, with every batch, you randomly reinitialize those weights of the initial layer. And so what you're doing is basically you're totally randomly altering the color scheme. So you might get images something like this, where we humans can easily recognize this as a face, but the color scheme is totally warped, right? So this is a kind of data augmentation, which interestingly, it seems to give near oracle performance, which means this is PPO, oracle performance is PPO trained directly on the test set. So near oracle performance means you're generalizing almost as well as if you could just train directly on the test set, which is quite good. Yeah, I wonder if this idea is more generally applicable as well. All right, yeah, we talked about competitions are being won with PPO still. Reward shaping is important. Obviously, this can make your problem way easier or harder. In this case, sometimes agents had to go up a ramp to find some food up there. And so what they needed to do is just give a reward for getting a bit of vertical, and that helped to encourage the agents to explore ramps. So how robust are RL algorithms? So this is related to generalization. In Atari games, Atari is actually totally deterministic. And so what Michael Littman found was that the DQN agent would be doing these amazing things, and deke here, the enemy goes by and dekes back. Like, how does it do that? Wow. Well, what it's actually doing is it's tried a bunch of things, and over time it has memorized a script of actions, right? And since Atari is deterministic, this script always works. And right, so he's come up with various levels of generalization. There's on policy, that's like, can you do the exact deterministic Atari game? There's off policy, can you cope with situations that, you know, a previous or a different policy might have encountered? And then there's finally, can you cope with basically reasonable environments, which are, you, given that Atari is deterministic or whatnot, you might never end up in that, you might never end up in that state, but it seems reasonable to a human at least. Can your agent cope in such a new environment? I think generally we do well on policy, maybe off policy a bit. So one of my last takeaways was that the coin run environments might be quite useful because they can be generated without limit, right? And this allows you to basically do your cross-validation and your tests, just like standard ML. Cool. All right. So that is all for this presentation. Thank you for watching, and I'll have some other presentations as well.